In this video, we're going to solve for exact differential equation. An exact differential equation is when you have a function which is m of x and y and another function which is n of x, y multiplied to y prime and is equated by 0. Basically, it says that the derivative of m with respect to y and the derivative of n with respect to x, and should those two are equal, we can call the equation exact. Basically, what you can do after finding the exactness is to find the function whose derivative with respect to x is the m part and the function whose derivative of y is the n part. And we can use that to come up with the solution, and it says that each of these functions partial derivative does have to be continuous in a connected region to make everything work out. So this is our problem for today, which is 2xy plus e to the y dx plus x squared plus xe to the y dy, and this equate by 0. So is this side is the function of m of xy, and basically the other side, this side, is the function of n of xy. So we have to find out whether these two is equal or not in order to surmise that this is an exact differential equation. So first, we have to find out the partial derivation of m in terms of y, which is equals to 2x 2x plus e to the y. So the other function, the partial derivation of n in terms of x, is basically equals to 2x plus e to the y. So what is this? They're equal. So now that we've established that they're equal, we can proudly surmise that this is an exact equation, exact differential equation. Now that we know that there is a function, a partial function which is equals to the m function, we can now equate 2xy plus e to the y to integrate in our preceding processes. Now we're not neglecting the n function. We're going to use that in order to cancel out like terms on later processes. Oh, I forgot the dx. And since we're integrating in terms of x, we're going to put a generic function which is g of y, since if we're going to put an x function, it will just simply go away. So integration of 2xy is equals to x squared y plus the integration of e to the y is equals to e x xe to the y plus the generic function which is g of y. So this is the complete equation, the first equation that we managed to create by integrating the function of m in terms of x. Now we're going to derive the given equation, the first equation, in terms of y. So x squared y plus xe to the y plus the generic function which is g of y. Now to derive this, x squared y will become x squared plus xe to the y. Now the generic function will have changes. It will become g prime of y. Now that we got the derivation of the first equation, we're going now to equate the function of n, which I stated earlier was not neglected. So x squared plus xe to the y plus g prime of y is now going to be used as a catalyst in order to cancel out like terms. I'm going to erase some of the space here. So using the resulting numbers or values, x squared plus xe to the y plus g prime of y equals the function of n, which is x squared plus xe to the y. And now we're going to cancel out the like terms that we saw. So x squared will phase out, xe to the y will also phase out. Now the remaining value is the generic function, which is g prime of y, which is equals to 0. And now to integrate this, g prime of y will become g of y, and c0 will become the arbitrary constant, which is c. Now we're going to use the first equation that we made earlier in order to substitute the generic function to the arbitrary constant, or the resulting value that we get from canceling out like terms. So x squared y plus xe to the y plus the substitute of g of y, which is the arbitrary constant c. Now for the final answer, we're going to transpose c to the other side of the equation. So x squared y plus xe to the y equals to the arbitrary constant, which is c. And now arbitrary constant are always positive wherever side they went. So this is the final answer. Thank you for watching, guys. Hope to see you next time.